All right, everybody, welcome to Class 6 of Uncertainty and Probability Theory, the Logic of Science. We finally are getting to probability today. Everybody's been waiting for us to get to probability. Well, what did we do? We started by trying to understand how we understand. We're talking about, in this class, how we know things. We're trying to separate our knowledge of things, how we know certain things, from the essence of things themselves. Both are important. We're not going to ignore the essence and metaphysics and all that kind of stuff, especially when we start talking about cause. But we're very much interested in our knowledge of things, which is entirely different. And I want to reemphasize the point. So we started with understanding logic and uncertainty. Not logic and uncertainty, logic, and how logic is itself formed from more basic means of intellection, which is to say our intuitions and induction and things that we must take on faith, things that we can't prove. We can't prove the rules of logic. We can't prove mathematical axioms. We can't prove any of that stuff except by recourse to our intellects, our inductions that we make. And last week we went over that, finally tied it all together and showing that there were at least 5 different kinds of induction, from induction, the pure induction intellection from which we derive these universal essences, from induction argument where we learn the rules of logic and then we say, yeah, these things apply, now we can become rationalists and all that kind of thing. Well, we did all that. And now it's going to become clear where all this was finally leading. But before we get to this point, I want to emphasize something again. We're talking about our knowledge of propositions, all right? Our knowledge of propositions. Not at this point, anyway, talking about how those propositions become true. So suppose we got a proposition D, whatever it is. We have a proposition D. We may know D is true. Now, how do we do that? Well, we might have some premises. Suppose we have 2 premises, P1, P2, like D might be that Socrates is mortal. P1 might be all men are mortal. Number 2, P2 is Socrates is a man, and therefore we conclude Socrates is mortal. Now, it doesn't have to be this particular statement. There are all kinds of propositions in the world that are true, but we can get to them in various ways. For instance, we may be able to know D by another path. We may have a list of entirely different propositions from which we derive this D. Now, this is exceedingly common in mathematics where no one even blinks at it. There's all kind of ways to get to prove certain theorems and so forth. Theorems are just propositional statements that we want to prove using arguments like this. But it's also true in real life, too. So, for instance, here's another one. We could reason all these out if we know all these other propositions and so forth. But if we don't know them, we might even have revelation from God himself, who told us that D is true, where R is our revelation premise. The point of all these things is that we don't say how D comes about true. It's our knowledge of what we know about D given the assumptions that we make. These are always the assumption, the premises that we're taking up here. These are what we supply. This is the subjective nature of logic, if you remember all the way back to the first couple of classes. This is the subjective nature of logic. All this part up here. This part, the connections from the premises to the conclusions, that is entirely objective. There's no subjectivity about that. That's fixed. Okay, we got to keep our parts separate. So later on, we're going to be talking about subjective probability and what does that even mean? All that kind of stuff, where all kinds of errors are made and ruin a form of probability. I don't like the way subjective probability works out because of that reason. All right, so we have all of this, and we're concentrating on the connections. Logic is just a connection between premises and conclusions. That's it. Logic is the connection. And now we're going to do this. Okay, so let me erase this. Now, I want to emphasize that point over and over and over again. The epistemology is not the ontology. All right? The way our knowledge of things is different from the things themselves, in and of themselves. We have to keep that distinction clear. It's not kept clear, and that leads to all kinds of errors in things like, they're going to call them hypothesis testing and the like. So, okay. That's the throat clearing. Now, again, we might have, let me just, of course, I can't, there may be, I think it's going to happen, we're going to get some upgrades to the equipment here, so you guys will be able to see and hear me more clearly. But let me just draw a couple of these equations on the board here. Finally, we're doing the math today. We're going to get into some math. Not very difficult math, but math anyway. All right, so we might have two kinds of propositions, which we've been discussing. Okay. I'll draw them both up and then I'll explain them. Well, it's obvious that we have some propositions, x being greater than z, that we know with certainty, given certain premises. So let's just think about this mathematical argument here. We have x, y, and z are integers. I'm just going to say they're integers. And we're going to say that we know that x is larger than y, and we know that y is greater than z. Those are our subjective premises. And from that, we can deduce that x is greater than z. That's a deduction. This is true, a conditional truth, a local truth, given these premises. We're certain of this, okay? We're certain of this local truth. But we also have all kinds of propositions like this. This is the first time we're seeing these kinds of proposition right here. So suppose there's this is the vast number. This is uncertain propositions are number. They're infinite in number, of course, but they are the ones that we deal with mostly in life. Okay, so we really need to understand uncertainty. Hence the name of the class. So a witness on a stand was giving testimony, for instance, and he said, I saw a bunch of guys come out of some store or something like this. I saw a bunch of guys. That was his testimony to the either the lawyers or the police or somebody like this. And from that, we want to know something about this proposition. There were 12 guys, not 11, not 13, not 9 or something like this. I want to know whether there was an even dozen people. Now, there's no way to get from here to here with any kind of certainty. Now, we could cheat. A lot of people do this, and they don't realize they're doing this. Well, they're going to say bunch means no more than 10, fewer than 10. Now, that's a tacit premise. If I stick this tacit premise up here, well, then all of a sudden we know that this is false. But that's not the way it is in real life. We don't know what the guy meant by bunch. You might have a definition of bunch, and you might survey all sorts of people and look at the variations in their definition of bunch, but that doesn't mean that that's what this guy had. So we're uncertain of this conclusion. Yet, this conclusion here is different than, say, this conclusion. I find this notation confuses a lot of people. 1e to the 6. This is the old-fashioned scientific notation. Number of zeros that you stick on the end of it. So this is 1e6 is a million. It's easier than writing a million sometimes, especially when we get into big numbers. So if we had this particular proposition we're interested in with relation to this evidence, well, that's entirely different. A bunch of guys, could it have been a million? Well, you could always imagine some scenarios where you're sticking in all sorts of tacit premises up here that are not part of the given evidence, but this one becomes increasingly unlikely compared to this one, given our standard knowledge of bunch. We're gonna have tacit premises of the word bunch up there no matter what we do. We can't escape that. But bunch is probably not going to mean a million. It's probably going to mean something more like 12. So we have uncertain information. Now, what we really want to do, if we want to do math on all this, we have to ask the question, can we put numbers to all this stuff? is there a way we could prove that we could put numbers to all this stuff? And not only put numbers to all this stuff, but we want to have these numbers be consistent and accord with common sense. In other words, if there's two ways, like I showed you in the original proposition D, if there's more than one way to get to a conclusion, and we want to and we know the conclusion has a certain value, a truth value, we want to be able to reason and apply numbers to these, such as these numbers are consistent. Now, we're going back to Jaynes. We're finally going back to Jaynes. We're going to do his chapter 2. We're going to start in chapter 2, the quantitative rules, he calls it, of all these things. So let me erase this. This stuff is just my introduction to it. This is not in Jaynes, but what I'm about to show you is. So I'm going to give you, I already gave you loosely some axioms by a guy named Richard Threlkeld. I always love that name, Threlkeld Cox. And he has a set of axioms about the evidence that we accord things and the numerical values that we might give them. And Cox has written a wonderful book, which of course I mislaid. I had it ready to go, and I don't know where I stuck the thing. The algebra of subjective something. Here we go. The algebra of probable inference. This book has the proof. Everything from the probability to entropy, and it's all in there. It's a very nice book. I mean, the proof on here, we're going to go through, we're going to sketch it. I'm not going to do the line-by-line proof. There's all sorts of websites out there. Even Wikipedia has a pretty decent proof of Cox's theorem. And it's been modified. Jaynes himself takes care to point out, we're going to use the differentiable version of the proof as part of our tacit premises. But there's others out there, a guy named Azcel, A-Z-C-E-L. I'm not certain how he pronounces that because I've never heard anybody say it. But there are non-differentiable, you don't have to assume differentiability of these functional equations I'm going to show you. And so we could derive all of these things. Now, there's other axioms out there, axiomatic approaches. We're going to start with some axioms again that we think that accord with our common sense, that we derive from our intuition, and we're going to build up from this using a bunch of premises we're going to drag in from mathematics that we already believe is true, and we're going to build up a very simple, depending on, simple's a relative term, right? We're going to build up a system anyway that proves that probability is a number. It's going to be a number between 0 and 1, and it's unique and consistent and all this kind of a thing. There are others, axiomatic approaches besides Cox's. That's my point. There's Kolmogorov. He's very famous. Gave them. But he sort of starts with the assumption. He just assumes. One of his axioms, that is to say, assumes probability is a number. Well, we don't want to do that. That's kind of an assumption that he didn't take as true. And the idea that probability is conditional is lost in Kolmogorov because they jump right to the math, right to this hardcore math, and they're off to the races to get the measure theory, if you know what that is. And it's all fine, no problem. But it misses the philosophical import, which Cox gets. And that's what we want to do with Cox. Because it turns out, like we've been doing these arguments, and we've been doing arguments like this. I'm going to show you the notation. We're going to do a change of notation. We wanted to know, just using A, B, C, and D. We have some premises C here. And we want to know whether the conclusion A and B. Remember, we're using the Boolean notation we went over briefly, and you should have done it as your homework. So this is A and B. The statement, the joint statement, A and B, is A and B true? Now, we can write it like this in the old-fashioned logical way that we've been doing up to this point, and there's no problem with that. However, that becomes difficult, and it's just notation. Once again, we need to avoid the deadly sin of reification. This is just notation. It's not the things themselves. It's just the way we describe them in notation. So this is going to be equivalent to that. All right? That's just another way of saying it. So we want to know what's the logical status of A and B given this information C that we assume. Now, here is Cox's axiom. I'm just going to read them out to you. They're very simple. They're exceedingly simple. The probability of an inference on given evidence determines the probability of its contradictory on the same evidence. So if we have a contradictory to this, we're going to have a function that gives us a value for this, and it's also going to give us a value for this. James uses, remember I told you there's all kind of ways to write contradiction or the logical contrary. So this is one way to write the over bar. And we don't write it over each one individually because it's the statement. It's the joint statement A and B. We have the joint statement here. In other words, if probability tells us something about this, probability is also going to tell us something about this. That's an assumption on Cox's part. That's an axiom. I can't see any problem with this axiom, and as far as I know, nobody ever has found a problem with that. Here we go. Here's number 2. The probability on given evidence that both of two inferences are true is determined by their separate probabilities. One on the given evidence, the other on the evidence with the additional assumption that the first inference is true. I'm going to read it again, and you might be pause or go back or something like this. The probability on given evidence that both of two inferences are true is determined by their separate probabilities, one on the given evidence, the other on this evidence with the additional assumption that the first inference is true. Now let me explain that in this notation. Sometimes notation is an absolute boon. It does wonders for us, and sometimes it's a stumbling block, especially on fine points. So right away we can see Cox used on the evidence. In other words, this is our evidence, the premises, the assumptions, all those tacit and implicit and stated premises and assumptions and arguments that we make. That's the evidence, okay? We can call all that stuff evidence. And of course, in statistics, it's always called evidence or observations and the like. Observations are just part of the evidence. We only make... There is no knowing a proposition's truth or falsity or anything in between without some evidence. In other words, it's going to turn out all probability is conditional. There is no such thing as unconditional probability. We're building that in from the start. And Kolmogorov does that too. I have that in my book, I think chapter 4, which we'll get to later when we talk more about the philosophy of these ideas. Right now we're just going to do some simple math. So let's think about this. I'm going to follow James more or less here, the first part of chapter 2. And does he use A, B, and C? He does. Okay. Well, all right. So we want to know. Now, there's two ways we could do this. We want to know this. We want to know the truth of the proposition A and B. We could find out, for instance, that we could start with this. We could start, well, C tells us that B is true. But this is C could be a whole, C is not necessarily a simple proposition. It can be a whole list, right? It can go on for pages like some mathematical proofs do and all this kind of thing. It in no way means it's simple. It is a stand-in for all the complexities we have in any argument. Okay. Now, supposing that C tells us that B is true, then we're going to use that information to tell us something about A. So we can start with this, and then we want to determine whether A is true, given now what we know about B and C. But we want to be consistent. Now this is Cox's axiom in play right here. We could also, we don't have to start with B, we could have started with A. And if C says A is true, why then we could form what we want to know about B from the knowledge we have assuming A is true. That's it. That right there is it. So now, this is the very simple, just starting out whether I want to know if this proposition is true given the evidence. And I could do it two ways. And from that, that turns out, if it's going to be if we haven't proved it yet, if probability is going to be a number, why then that's going to be a function. Probability is going to be a function of these two things. That's what Cox's axiom said. So we can write it up. Let's see, B, C. Sometimes Janes will also put additional parentheses. I could have put parentheses around the entire block, the logical block, if you like. I could have stuck them in there. Parentheses, of course, in notation, are just there to help keep things straight, just so we can sort of keep track of where we are. They're not necessary, and I think on a board, on a chalkboard, they clutter things. On paper, though, when you're writing it out in LaTeX or something, they're much more helpful. But I think on this board, we don't need them. So that's a change in notation. Okay, well, so that's going to be our functional form. The key word being functional, as we're going to see. All right. Unfortunately, I'm running out of board space, so I'm going to erase all this. But I think you get the idea about this. Okay. Maybe I'll erase the whole probability thing too. Give me some more acreage. Okay. Now, if we learned some new information, and that new information gives us more certainty about B, this will be the case. Our original list of premises was C. Remember, that could be a huge thing. That could have observations in it. It can go on for miles. But there it is, C, our premises. We learned some new information. Now we say that B is more plausible. This is what we'd like to have happen. We'd like to have this equation happen. All right. Then it's going to be... this is the case. So this C only tells us whether or not B is true, or gives us information about B. It tells us nothing about A. This is just another assumption. All right? And if that's the case, why then it must be that this is the case. This is greater than equal than my handwriting sort of stinks. We're assuming here that these are our two new assumptions right here. We're just bringing these in, but we can deduce this from these two assumptions. We say we have new evidence coming in, this C, which is going to change C in some way or another. It could also be a removal of C, you understand. It doesn't have to be that we're adding a new premise onto C. We could be excising one or some or any of the ones inside C. Okay, and now we're also going to assume that it doesn't say anything about A, because that could also be the case. So this would be the case, if that's true. If this new evidence doesn't change anything, this is going to be the case, because we're assuming B is true on the right hand. That's one of our premises, right? So we're assuming B is true. Everything on the right, in a local truth that we went over, I maybe didn't emphasize this enough, but everything on the right side of the bar is an assumption. We're assuming on this side over here that B is true. B is true, we assume. And C is also true, we assume. And here we have new information, but this new information we're assuming, only says something about B, but we're assuming B is true, so it doesn't matter. So this right here this equality would hold. And from that, because we know that B could be more plausible given this new information, this has to be the case. A and B given C prime, prime meaning the new information, is greater than this. Okay. Well, we could, it could be the same way. So this is just, what we're trying to do here is we're trying to form, using just logic and those two axioms that we got from Cox, we're trying to build up this equation that proves probability can be a number, okay? So we might have a different 2 primes, meaning a different form of C entirely, that doesn't change, and that's easy enough. We could always, it doesn't change our knowledge of B. That's easy to do. All we have to do to change C to not change our knowledge of B is just add any necessary truth to the list of C. Any necessary truth, 1 equals 1. Well, that's a true statement. We can add that to C. It doesn't change whatever B is. It's not going to change our knowledge of B, so that kind of thing is certainly possible. And we're going to assume that we're going to assume that it has something to say about A. So assuming B is true and given this new information, that's going to tell us something about A. We're now going to say that A is more plausible by whatever this new thing in C is. So that's going to be true. All right? Now, we have that functional equation, which I'm going to write back on the board. Oops. Yeah, I'm doing my parentheses wrong. Okay. Which equals, if it's going to be numbers, we'll use small. This is a standard way to do notation. We use these small Latin letters at the far end of the alphabet to indicate numbers. We're going to use capital letters usually at the beginning part of the alphabet to indicate propositions. Later on, we'll use Greek letters in the same kind of way. Lowercase Greek letters will indicate unobservable parameters and all this kind of a thing. So this is just, again, a way of doing notation. And it's just going to keep track because I want to have, I'm not assuming, I want to see if I can prove that I can get these things to be numbers. And so if they are going to be numbers, we can write it like this. This is just an easier way to doing. Now James assumes differentiability about this, which means, for instance, the partial derivative with respect to the arguments is going to be what we want to have is continuity and differentiability, so that we have a small change in information. We want to have that information change the probability. And see, this is where I struggle because I don't know how much math everybody in the audience has. I'm assuming some people are craving for the math. I assume they have a lot, and some people will have virtually none, and I don't want to lose them either. But basically, in words, all this says is, if I look at how this changes with the information, any change in here, any change at all, is going to make a change in the number. And it's differentiable, meaning it's smooth, and the function itself is smooth. There's no jumps or something like this. The equation is not complex or weird. Everything can be drawn smoothly, if you like. I'm just trying to put this in ways that people can understand without having the math. However, this assumption here, this is in both parameters. It's fx is like this and fy is also like this. This is not necessary. Cox uses this assumption, and that leads to a very simple proof and entropy and all this kind of a thing. But we don't need it, okay? It's just a simple way to do it. And there's been so many people who have tweaked Cox's theorem for various situations in thinking about continuity in the real line and all this kind of very complex mathematics that don't concern us here, because what we're really trying to get after is, can we put this to be a number? Okay. All right, so let me, there, I stand out of the way in case you need a screenshot. Okay. So far, we haven't done very much. That's the problem with math. All I've done is just showed you if it's going to be a function, if probability is going to be a function of some kind. This is the shape it has to be. That's all we've done, and that's all we're going to keep doing for a little bit right here. We haven't yet proved it is going to be a number, okay? So let's continue doing that. So the way we did this before, I just did A and B, but this should work. Consistency means this should work no matter what our evidence is or no matter what the form of the proposition of interest is. So it should work like this. That would be right? Now I have a more complex proposition here, A, B, and C. That means they all three have to be true together, given some new premise D. And I could, if it's going to be a number, it's going to look like, well, I could just bust it out like this. It's no problem. Oh, BC, I'm sorry. It is a problem. I looked at it and I thought, what the hell's wrong with this thing? You guys should catch me on this. Somebody should come from the future, come back and correct me on this. I thought something was weird about this. I lost my C. C is one of the things we have over there. So I'm going to take this as if it were the old B, and the A just stays A by itself, okay? So we have that particular form right there. Well, now this right here can be, it doesn't matter whether, for some reason when I was first learning math a million years ago, when I saw curly braces, and people use these curly braces for weird sets and all this kind of thing, and the curly braces threw me off. I don't know why. They intimidated me. I don't. It's a purely aesthetic thing. Notation is aesthetics. Okay, that's what I've been trying to emphasize. And whenever I see curly braces, it sort of gets me somehow. And I think something magical is going on with this equation, rather than when we just have the curved ones or the square edged ones or something like this. It's a mental block on my part, but that shows you how notation can affect you. Well, see, I was going to tell you an anecdote about my number one son, but I'll let it pass. I remember, though, when you're in class, that's the best classes is when you can divert the teacher or the professor into some anecdote and stop having to do so much learning. But I won't do that to you. Okay. So what I'm going to do is treat this in the way we treated the first time. So in other words, we said that things like this could be like this. A function of C given D and B given C and D. So there's the function. And that's just the A and the B, C, D given along. No problem there. Or we could do it like doesn't matter which order we take these things in. So we could just do it. We could do it by CD or BD, whatever. It doesn't make any difference. So this equals a function like this, just to make it. And that's what we wanted. Because it doesn't matter which order we do these things in, we can write this stuff, it's all symmetric. We now have what is called a functional equation. Da, 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 da. And a functional equation is of numbers, and we can start with this and prove what kind of shape this functional form has. That I won't do for you. That I'm going to leave to Cox's thing. James has it in a couple of papers. I'll put up the Wikipedia link too. That does a reasonable job. It's one of these things that's not political until they discover people like us are doing it. Maybe they'll change the proof on us. But it's functional equations. If you know them, you can stare at this and you say, aha, all right, I know how to go about doing this, even if you don't have the proof in your head. But if you don't, it's just what kind of a function would look like this? That could take a function of something, another function in a number, and be symmetric in that and these arguments like this. And it turns out, well, it turns out to be probability. So let me give an example. So yeah, you have all that on the board there, and get out of the way to take a screenshot. Okay. And this is where you have to take on the appeal to authority. Unless you do it yourself, that'll be one of the homework questions for those who can do that kind of a math. That functional equation can be proved to have a certain shape, a certain mathematical form. And that mathematical form turns out to be probability. So it turns out James first uses a W just to keep you on your toes. Well, I'll write it up the way he did, and it's worth probably going through just a little bit slowly, because the problem is you never know how fast. I really don't know how fast I'm going compared to how slow or quick your ears are taking all this in. So, all right. Which equals it turns out this functional form gives us things like this. This function W is no longer a functional. It's just a regular old mathematical function. You know, you remember the functions from back in. If you don't remember this, a function. What's a function? You know, you had a function of x. Could be just x. And you're going to draw that. You know, f of x looks like a straight line on a graph, something like that. That's the type of function I mean here. All right. Well, you could take A given B and C are true, and it's going to turn out to be multiplied by, it's going to be turned out to multiply by B, assuming C is true, and that's equivalent, since it doesn't matter which way we go, to calculating the function for B given A and C are true times the probability of the function that A is true given C. Now, if you've seen this before, it is Bayes. There we go. There's Bayes. It's not quite Bayes yet because I haven't showed you the number. We now know it's this is the functional form. We haven't yet. Now we're going to prove. We know from the functional form it is a function of this shape. Okay? So we've proven from the functional form that it is a function. Probability is a function like this of this shape. That's the proof I left out. Now we're going to prove that it's going to be probability, and it's going to live on 0 to 1. Okay, so that's now let me just go through that again. We started with logic, and we started with simple axioms, and we said if probability is going to be a number, it's going to be of this functional form. That particular functional form has only one solution. It's a unique solution, and it turns out to be this function. And this function has this shape. Now we need to learn what numbers flow from this function, this shape of this function. Okay? And the whole point of it is it's going to be 0 and 1. There's no mystery to this. We see right away, though, we get Bayes' formula right out of this. Bayes on day one. We don't have to wait for a long time to get to it. It just pops right out. This is Bayes' formula as a direct result of assuming probability is a number. So here we have Bayes' rule, which we're going to go over again. So if you don't see that and you don't understand what I mean by all that, don't worry about it. But if you have seen it before, there it is. It's just Bayes for you. Okay. Now, now I'm going to suppose. So now I want to show. Now our job is to show what numbers. What's the range? Where does this function W live? Okay. We're going to suppose. F A B C equals B and C. I'll write it all up and explain it. We're going to suppose that C tells us that A is certain. Just a supposition. This is, if it is true, it's just a premise that we have that C tells us that A is a local truth. Could be even a necessary truth. In any case, a truth. That means this must be the case. That the numerical value, whatever we're going to do, whatever numerical value, we already know we're going to get a number out of this. So now we're perfectly allowed to say this is going to be some kind of a number. It's going to equal this kind of a number. Because C already said A is true, so that the value of this has to be the same as this value, right? Because A given C is true, and so whatever the value is here, it can't be changed. And this also has to be the case because we know that it's true that A given C is true. We've assumed. Adding a list of premises over here, as long as B is not contradictory. Of course, this is James I forgot to bring up. This has to be the case that the value of A given C, no matter what other premises we stick in here, as long as they don't contradict C, don't change the numerical value of this. I hope that's easy to see. So in other words, I've already assumed we're starting with this premise over here that C tells us A is true. Local truth, necessary truth, doesn't matter. So whatever the numerical value of this is going to be, it doesn't matter if we stick other premises on here. We already can deduce A from C. And of course, probability breaks down when you stick in contradictory. I mean, you can come up with you could say for a list of premises, suppose A is true, and suppose not A is true. And therefore, what's the status of B? Well, that's nonsense, okay? So we're not going to do that kind of thing, and that's one of the rules. James calls this a robot. I think that's okay. It's fine to have a robot. Once you have all of the stuff written down and everything, a robot, a computer, anything, can go ahead and calculate all this stuff. But it misses that element. James's robot misses the element of subjectivity. Because in real life, not these kind of things, we're still showing the shape of all this, but in real life situations, it's always us, it's always we who give those subjective premises, not subjective probability. Okay, so, with these restrictions, supposing this to be the case, then it's going to be the case from knowing this functional form that the value of BC has to be this value times this value. If we just draw this right out of here, right? We just draw this completely right out of here, as I hope you can see. So WAC, because AC is the same as A given BC, A given BC times WBC must equal this, WBC, which in our case, AB given C. That makes it a little bit easier. WAB and C, that's one of the things that we came up with. James was a genius. And not for the first time you'll find mathematicians have a joke. It is easy to see that, they move from one step to the other, and what's hidden in that is easy to see that are 42 pages of stuff. All right, so James has that problem where for him it's very easy to see. For the rest of us, we have to sort of stumble along. But let me go through it all again just to make sure you are with me. I'm going to suppose as a premise, and remember our goal. We already know that probability is a function like this. Now we want to see where the function lives. What numbers can we assign to this? We're going to suppose, if this works, which we know it does, we proved through the functional analysis, we're going to suppose that this is certain. A given C is true. It's just true. And therefore, it must be that this value, whatever the probability is going to give us, must be this value. Because we already know A is true given C. So this is just a matter of pure logic. And it's also the same here. It's a matter of pure logic. A is true, we already know, given C. And adding B to the other side does nothing, so that has to be true. We know this is true. We know this function up here is the proper shape of probability. And so we start off with this, AB given C. Well, not AB given C Well, that's the same as B given C. We prove that up here. That's deduced, supposing this is the case. And that equals, well, that equals this times this. Well, here's that part, the B given C. And A given C is usually written as A given B given C, but that's the same as A given C. So here is, in simple algebraic numbers, if you like, we have x equals y times x, if you like. And that must mean that with certainty, y equals 1. So, because we know this is certain, probability of a certainty, whether it's a local truth or a necessary truth, some kind of truth, is 1. Okay, so we got one bound on the probability. The other bound is going to be 0. As I've told you, it's no secret. I am not going to do it for you. It involves an analysis just like this. There's absolutely no point doing it twice. I'll leave it as homework. It follows these exact steps with with the assumption. Well, I'll leave that to you. You can find. I'll try to find a link to Jane's. There's all this. If you don't have the copy of Jane's, there's all kind of copies floating around on the interwebs. So you might be able to locate her. If I can find one, I'll put it up. Okay. Now, we finally have moved to probability. We have proved, and not assumed, like Kolmogorov has, that probability is a number. That number lives between 0, which is falsity. It can be a local falsity or a necessary falsity, to certainty, 1. Probability is an extension, therefore, of logic. We've done everything logical. Everything is a matter of logic up to this point. That's all it is. Probability is the relation of the evidence to the proposition of interest. How certain the evidence is, given the It is how certain the proposition of interest is given the evidence. That's what probability is. That's the definition of probability. It's how certain the proposition of interest is. In other words, it's how certain A is given the evidence B. It has nothing to do with subjectivity. It has nothing to do with relative frequencies. It has nothing to do with plausibilities and all this other stuff. We're going to go through all that in depth, I promise you. We've already proved it isn't, but I'm going to go through it all in depth to show you that it's really true. I'm going to show you how these other interpretations can't possibly be right. This is the interpretation of probability. It's how probable this evidence is given this evidence, or how this proposition is given this evidence, or premises, or list of assumptions we make, whatever you want to call this kind of a thing. That's probability. And it lives in 0 to 1. That's it. That's probability. So, I'm going to erase this because I need the board space. And it's going to form the basis of your second homework question, which I'm going to steal from Larry Brettenhorst. He was the physicist who edited and edited James's work, because James died before he finished the book. And so he got the book in shape, and he added a few homework questions in some of the chapters. There's not a lot of them. In fact, what I should do in uncertainty is what we're doing here. I should give you a lot more of them to make it much more like a textbook. That's easy to do in math. It's not as easy to do in philosophy, because if I'm talking about the philosophical interpretation of something, well, you could posit it out and you could write it out, but it's not going to come to some equation where x equals y or something like this. Okay. Well, so we've learned right away, because now we're going to see Bayes again. Let me write it up and I'll show you. We had W over 4. That was that function, which we now know we can call probability. There's various ways to do probability. James uses a small p, lowercase p. I like the capital PR, and I'm going to always use that. In LaTeX, it's just a slash PR. And the reason for it is because it signals its probability. It signals more than it's again notation. It's a matter of choice. There's no reason one way or the other, but it always tells me I'm dealing definitely with a probability here and not some other kind of weird thing. Okay, so here that's W again, now rewritten as probability, and that's Bayes. That's Bayes' formula right there. Absolutely Bayes. We get Bayes right away. We don't have to do anything special to get to it. And we see everywhere. I'm going to admonish you over and over again. I don't know how long I've gone on already. This is probably going to be some ridiculously long video. All probability is conditional on the evidence that you assumed. Like all arguments are conditional on the premises that we assume. That's what we did from day one. Probability is the same way. We cannot write. It is forbidden for you to write. Oh, I think that red. I used that red, and I noticed it didn't quite come out on the camera last time. Never do this. Never write probability of something without the conditions. There's no conditions here. There is no such thing. Such a thing doesn't exist. Yeah, if you're doing some proofs, you're writing down your head. It's a ponderous thing to keep writing, given C, given C, given C. It's a pain in the butt. Fine. But when you're trying to communicate to others, you've left the conditions out. There is no such thing as a probability. Nobody, for instance, has a probability of being struck by lightning. It doesn't make any sense. Right now, what's my probability of being struck by lightning? Quite different than if I'm on a golf course in a thunderstorm. Right? So the conditions change, the probability changes. Don't write like this. There is no such thing as unconditional probability. We get that already too from Cox. As a deduction, we deduce this. So all these controversies can be allayed if we'd started with Cox rather than Kolmogorov. But mathematicians love their measure theory, so okay. That's one of Cox's first axioms right here. So we have the probability A is true given B, and here's the contrary of A being false given B. We now know that has to equal 1. And that's very nice. And we have Bayes' theorem, and we have this particular thing. From these two things, we can deduce all the probability rules that we're going to start working with. That's kind of fun. Everything we know from probability we can deduce from these two things right here. Neat, right? Okay. I'll do one, and then I'll give you one for homework. I think I've gone on too long anyway, but I haven't the slightest idea how big this is going to be, but here we'll go. People wanted math, and we're getting it, boy. Okay, so it works for any. Remember, this is a matter of logic, probability. We have deduced as a matter of logic. So it works for any logical propositions. Whoops. There I go. Here is our proposition written in Boolean algebra. This is not high school or middle school algebra, whatever you want to call it. This is Boolean algebra. It means A or B. The proposition taken as a whole. A or B is true. If A or B is true, the proposition as a whole is true. Okay, that's back to Boolean algebra. All right. Well, that's going to be, we already know. More just simple Boolean algebra. If A or B is true, well, then it's the opposite. The contrary of that is A and B together. A and B, the logical and, is false. Simple matter of just pure Boolean algebra. Okay, now, well, we could write this equation as using Bayes. The first, I just erased it, but that's just using Bayes. Remember how we can bust this out, right? A given C times the probability of B not given A not in C, or the contrary of A, however you want to say it. All right, well, now from that we can go, let's make sure I'm doing this right here. Because it's symmetric, we could have started with B as opposed to A, and sometimes we do, and I get confused which one I'm doing. And here all we've done is just rewritten this part of the equation, and we've taken this. Well, the probability of B not is going to be 1 minus the probability that B is. Not is. That's not very funny. But that's the joke. Okay? Now, that is very simple. There's a step here. I'll leave that as homework. I want you to show how we get from this point to this point. Some of you it'll be blatantly obvious. Others might have to work at it for a second. Just a couple of lines of the high school algebra. But in any case, this is what we get out of it. We have this formula results. So now we have the probability that A is true plus the probability that A not and B. So A is false and B is true together. And so forth. Now that gives us, we're almost done. Here I just used Bayes, kept this, used Bayes for this. We're almost there. And I'm going to use the opposites again. This is the same as that. And I've run out of board space. So I'm going to just erase this and write up here, because that's going to be what the equality is. And that'll be the fun part. Last line. It's going to be probability of A given C plus the probability of B given C minus the probability of A and B given C. Aha! And this is called, so this is just from this, probability of B, and then the probability of A and B given C we subtract off. This is called, in all probability books, the sum rule. We have just deduced the sum rule using Bayes and the probability of two things, itself and its contrary must sum to 1. That's directly from the algorithm, or from the Cox's first axiom. Well, we're going to see if we can generalize this as part of the homework, and we're going to know if we swap this around, we put C given A and B, can we develop such a formula? And that'll be for you to decide in your homework. And that's it. So what have we done? We've done quite a lot. We have proven that yes, indeed, probability can be a number, and that number must live between 0 and 1, and that all probability is conditional. And there's no way to do a probability that isn't conditional. That probability is a matter of logic, strict logic. And then we've developed some very simple, Bayes rule popped out, the contradictions popped out, we have the sum rule that pops out. Everything is going to pop out from this. Next week, we're going to go over some of those other things that do pop out of this, and we're going to build and build and build until we have quite a mess in front of us. That's the only way to put it. That's it. The homework, I'm not going to write it up, okay? You have to look to the class notes, which will be on the page, the wmbriggs.com class page. The link will be right there. It's going to be in the description below in the video, or if you're already on the page, you'll see it. And that's it. Until next time, good luck with the homework.